When executing heavy data processing workloads, systems engineers frequently mount cloud storage buckets directly to their active compute instances. To make this connection, they rely on abstraction layers, most commonly Mount Point for Amazon S3. Suppose you initiate a routine data transformation, like using FFmpeg to convert an MP4 video into an MP3 audio file directly on that mounted storage. The process starts, processes the data, and throws a fatal error the precise moment it attempts to write the trailing metadata and close the file. Execute that exact same FFmpeg command on a system running the Amazon S3 files architecture. The conversion processes the data, appends the metadata, and cleanly completes. Legacy mounts merely simulate a file system directory over an object store. S3 Files replaces the simulation with a true file system endpoint, altering the I/O behavior at the architectural level. This illustrates standard Amazon S3's architecture. Standard object storage operates exclusively over HTTP, meaning files are immutable. Modifying an object requires a complete HTTP put request to swap the entire file. But FFmpeg expects byte-level control to seek backward and append trailing metadata. You cannot execute precise POSIX file system append operations on immutable HTTP object storage. Abstractions break. Resolving this impedance mismatch requires an intermediary layer capable of managing true block-level state. This maps out the S3 files architecture. It physically inserts an elastic file system layer inside the virtual private cloud. The compute node no longer speaks HTTP to the object store. Instead, it maintains a network connection to the EFS layer over TCP port 2049. EFS provides native, high-performance POSIX compliance. It supports seeking, appending, and directory management. The compute node writes its segmented data blocks directly into the EFS volume, executing the metadata append smoothly. This direct interaction with a POX-compliant layer is why the FFmpeg conversion succeeded in our test. The compute resource is isolated from the object store. It interacts exclusively with a high-speed local block cache. Placing a high-speed cache in front of persistent storage introduces an immediate engineering risk, maintaining state synchronization between local modifications and the permanent bucket. This detail shows how S3 Files tracks unsynchronized local modifications. Any file modified in the EFS layer, but not yet pushed to S3, is tagged as dirty. A background synchronization process continually monitors these tags and copies the modified data from the local cache to persistent storage. Once the state is verified in the S3 bucket, the system clears the flag. Despite the caching layer, the S3 bucket remains the absolute permanent source of truth. This eventual consistency model decouples the local speed write operations of EFS from the infinite scale of an S3 bucket. Running arbitrary large workloads exclusively on EFS carries steep cost penalties. Conversely, standard S3 suffers extreme latency drops when forced to handle thousands of tiny files. This routing tree visualizes the first rule of S3 Files: eager loading. Files under 128 kilobytes are intercepted and pushed directly into the EFS cache. This rule applies to directory metadata, allowing operations like ls to execute instantly from the cache. But routing multi-gigabyte video files into the EFS cache would be prohibitively expensive. The second routing rule is the 1 megabyte bypass threshold. For sequential reads, massive data blocks bypass the EFS cache completely and stream directly to the S3 bucket via standard HTTP. Bypassing the intermediary prevents massive payloads from filling and polluting the local cache. The intelligent routing acts as an automatic arbitrator, enforcing POSIX speed for metadata while maintaining HTTP efficiency for large objects. Because the system relies so heavily on precise caching protocols, it is ultimately bound by very strict physical and geographic limitations. The compute node and the EFS endpoint must reside within the exact same AWS region and VPC. Attempting to mount this file system from an external cloud provider like DigitalOcean or Hetzner entirely defeats the design. Stretching the network connection geographically introduces latency penalties that completely erase the speed advantages of the local block cache. S3 Files is a localized AWS architectural optimization, not a global file sharing protocol. This hybrid architecture targets very specific production environments. This diagram outlines an ideal use case: AI coding agents, and autonomous testing tools interacting with the EFS volume. Autonomous agents constantly execute rapid file manipulation. They write logs, alter configuration files, and compile scripts in chaotic bursts of I/O. The local EFS cache layer absorbs this high-frequency volatility without triggering the latency of HTTP object replacements. The agent iterates at local hardware speeds, while the final compiled state synchronizes safely to the S3 bucket in the background. Machine learning pipelines processing thousands of small training data files use this identical approach to bypass HTTP overhead. By isolating the impedance mismatch between protocols, S3 files merges the interactive speed of legacy block storage with the infinite capacity of modern object storage.